All right, so one of the important things that I've sort of been hammering over and over again when we talk about constructing structures of molecules are these simple rules in organic chemistry where carbon likes to have 4 bonds, nitrogen likes to have 3 bonds, oxygen likes to have 2 bonds, and hydrogen and the halogens like to have 1 bond, right? Hopefully we've gotten all those rules down. But most of the times when I would state those rules, I would sort of preface it or add the little caveat of unless there's a formal charge. Okay, so this is specifically what this lecture is going to be devoted to, are situations that will arise when we'll see formal charges and thus will break from those rules. And these will sort of be the only ones that are allowed. Okay, so there might be other situations that would lead to a formal charge, but they're not necessarily allowed, like they don't actually exist in organic chemistry. So we're going to see the ones that really do. So the first situation here, carbon, of course, usually has 4 covalent bonds. This is a situation called a carbocation, where your carbon actually only has 3 bonds. Okay, 3 bonds and no lone pairs. So if we counted, carbon only has 2, 4, 6 electrons in its octet right now. So it does not have a complete valence. Okay, this is something that's relatively unstable, certainly way more unstable than if it had 4, that there was a 4th hydrogen on there, but nonetheless turns out to be a very important intermediate in a reaction, something that exists for only a small fraction of a second, but nonetheless plays a very important role. Okay, so first of all, let's make sure that we can calculate the formal charge on this, right? So just to practice from our Lewis structure, remember we're going to take the formal charge as the number of electrons carbon has when it's all by itself in its valence, which would be 4. And we're going to subtract the number that's sort of associated with this molecule here, counting only 1 electron for each covalent bond, which is 3. So this is a formal charge of +1. Okay, so a carbocation is a carbon with a +1 charge. Now, one of the things that we will see with organic chemistry and bond line structures is we ignore, or we rather don't include any information about lone pairs of electrons, and instead we only put formal charges in there. So you have to sort of deduce information about lone pairs from that. There are no lone pairs here, but this will be our first example of sort of working backwards to figure out what's going on by just given the formal charge. So in organic chemistry, you'll be given a structure like this. And the question is, well, what is the formula for this, the molecular formula for this compound? So I still need to go in and figure out how many carbons and hydrogens there are. Well, of course, at these endpoints here, we have carbons. At this intersection here, we also have a carbon. Each of these ones on the outside, I can decorate with 3 hydrogens because I have to complete this octet. But now we get to the new thing here, which is the carbocation. And what you have to know about a carbocation is it only has 3 bonds and no lone pairs. So that means that there are no hydrogens associated with this carbocation here, this central carbon. So then this would be C4H9, and then I'd have to give it that plus. Okay? Likewise here, same sort of idea. Everybody take a second and see if you can't get the molecular formula for this compound. Okay, so the important thing to note is that it's a carbocation. We know that because of the positive charge. So then we know that there are only 3 bonds. 2 of them are explicitly pictured here, but 1 hydrogen atom is also bound to this carbon. There has to be 3 bonds, so we're missing a hydrogen there. And likewise, if it's a terminal carbocation, you would know that there are 2 hydrogens associated with that carbon. All right, so carbocations are something that we will see. Another thing that we'll come across is what are called carbanions. Okay, so again, this is the Lewis structure for a carbanion. Let's calculate the formal charge here. How many valence electrons does carbon have when it's all by itself? 4. And then we're going to subtract the 1, 2, 3, 4, 5 electrons associated with carbon in this Lewis structure, giving us a formal charge of -1. So carbanions have a formal charge of -1. Notice that this does have a complete Lewis structure. It just also has a formal charge associated with it because it has that lone pair as opposed to being a fourth bond. Again, you'll hear me say this over and over and over again. Atoms don't like charges, right? So this is not like a super duper stable thing. You're not going to be able to like find this lying around in the cupboard, but it might be something that is an intermediate in a reaction and still plays a really important role. Okay, so the importance of this slide is to illustrate why you have to draw in your formal charges. Okay, so if we had something like this molecule here, we would have no idea really what was going on with that nitrogen, whether it had 2 lone pairs and thus a negative formal charge, 1 lone pair and a positive formal charge, or for whatever weird reason, had this half-filled orbital and thus had a formal charge of 0. Right, so the drawing at the top is sort of ambiguous because it doesn't tell you what's going on there. We could either draw in the dots or the charge, but for bond line structures, it will always be the charge, and then you'll have to work backwards to figure out what the number of electrons are. I will say though, for this one, nitrogen never breaks its octet rules, so these structures right here don't really make a ton of sense. It would definitely be this one. But nonetheless, if you don't draw a charge on if you don't draw a formal charge on a structure that has one in my class, it's going to be wrong, right? Keeping track of charges is a really important skill. So of course you can always work backwards, right? So if I had something, and we'll just take that carbanion, and I didn't have any electrons drawn, but I knew there was a formal charge of -1, then I could just work backwards from my formula here. Formal charge equals number of valence electrons minus something. I know that formal charge is -1. So that means that my x here, x would have to equal 5, and that could tell me to put in the dots, right? By far the easiest is there are only a few scenarios, and so it should just be easy to recognize the patterns, okay? So for example, carbon with 3 bonds and no lone pairs, positive. Carbons with 3 bonds and 1 lone pair, negative, right? And then carbon with 4 bonds has a formal charge of 0. Likewise, with nitrogen and oxygen, it's sort of the same idea. You can pick out these patterns pretty easily. Let's start with the base one that we know about, which is oxygen likes to have 2 bonds and 2 lone pairs. When it follows that rule, that means that there will be no formal charge. Okay. Now, if I remove a bond and instead replace it with a lone pair, such as the example here, that would give me a -1 formal charge. So that's 1 bond and 3 lone pairs. And then we could go the other extreme where we added a bond and took away a lone pair. So an oxygen with 3 bonds and 1 lone pair has a +1 formal charge. All right. And this should hopefully sort of make sense if we just compare our negatively charged oxygen with our positively charged oxygen. Which one looks like it has more electron density, right? The one with 3 lone pairs, not the one with just 1 lone pair, right? And that's what these species are going to be important for. They're going to be carrying excess charge if they're negatively charged, or have a deficit of charge or a deficit of electrons if they're positively charged. Likewise, we can identify a similar pattern for nitrogen by, again, remembering the base sort of thing here, where nitrogen likes to have 3 bonds and 1 lone pair. That would be no formal charge, a formal charge of 0. So then if we add a lone pair, take away a bond, that would be a negative formal charge, right? So this is a nitrogen with 2 lone pairs and 2 bonds, has a -1 formal charge. And the other extreme, it has 4 bonds and no lone pairs. And again, this should sort of make sense just by looking and thinking about electron density. Obviously, the more lone pairs, the more electron density is sitting on that atom. One important thing that I want to state outright here, different from carbon. A carbocation is kind of weird in that carbon doesn't have a full octet. Nitrogen and oxygen will never break their octet. So you will only see situations where oxygen has a formal charge of +1 but still has its full octet, or has a formal charge of -1 and still has its full octet. Nitrogen and oxygen always will have their full octet, so just keep that in mind. Okay, so next we'll be talking about resonance, but first make sure that you practice your formal charge, being able to compute it. Most importantly, I think, are these patterns, right? To the extent that you can just recognize these patterns, it'll make your life a lot more easily than having to plug into that formal charge equation.